Alright, so this is my video reassessment for our latest standard, which was Langrangian with forces of constraint. I chose a homework problem from the book. Uh, very similar to the problem which was on the standard, but each problem from the homework was similar to the problem on the standard. So, and I also want to give credit to the fact that it's a lot more detailed than the problem on the standard. The problem on the standard basically just asked us to find the tension force by using the Langrangian multiply. This one asks for a lot more. So basically just getting into the problem. Basic problem reader, mass M1 rests on a frictionless horizontal table. Attached to it is a string which runs horizontally to the edge of the table where it passes over a frictionless small pulley and to where it supports a mass M2. Uses coordinate x and y, the distances of M1 and M2 from the pulley. These satisfy the constraint equations. F of xy is equal to x plus y, which equals a constant. Write down the two modified Lagrange equations and solve them, together with the constraint equation for x double dot, y double dot, and the Lagrangian multiply lambda. Use equation 7.122 from the book and the corresponding equation in y to find the tension forces on the two masses. Verify your answer by solving the problem by the elementary Newtonian approach. All right, so just getting into the problem, and I'm gonna kind of speed through this because it's kind of lengthy. All right. All right, so basically this is just a diagram of, what the problem is asking. Basically just drew a diagram of what the problem states in the question. I'm gonna start over here. Basically when I just, just start off originally, how many degrees of freedom does the problem have? The problem originally has 2 degrees of freedom, but when we add in our equation of constraint, we get down to 1 degree of freedom. But like any other Lagrangian problem with constraints, we want to basically get that back to, we want to basically add a degree of freedom, as you put it. So basically when we think about our force of constraint, we have x plus y minus c. Because basically we say x plus y minus c equals 0. So therefore our force of constraint is x plus y minus c. All right, so basically just our Lagrangian is equal to the kinetic energy minus the potential energy. Going through all that, that's kind of simple. Here's our end product Lagrangian. This is the kinetic energy, this is the potential energy. And all right, so then basically we have our modified Euler Lagrangian equation when we're dealing with forces of constraint. And I ended up getting that basically lambda is equal to mx, it's m times x double dot. And also over here, I also get this equation for lambda by using the other modified Euler Lagrange equation. So therefore, basically our problem asks for x double dot, y double dot, and the Lagrangian multiplier lambda. We don't have those, but we have our 3 equations which can help us get those. So just moving along. Once again, this is my this is basically just using my equation of constraint to relate x double dot and y double dot. So okay, first of all, I basically just use algebra techniques. I compare the two Lagrangian multipliers lambda, basically, and I put the second one, I put y double dot in terms of x double dot, and then I just solve for x double dot. So that's the first thing that the question asks. It says write down the 2 modified Lagrange equations, which I did in the last page, and solve them for x double dot, y double dot, and the Lagrange multiplier. So that's what I did here. So this x double dot, this is my equation for the acceleration in the x direction. This is my equation for acceleration in the y direction. And this is my 2 equations for Lagrange multiplier. Both of them the same thing, so it really don't matter. Just one is in terms of x double dot, one is in terms of y double dot. All right. Moving along, the next thing the question asked me to is, it says use basically equation 7.122 from the book and corresponding equation y to find the tension forces on the two masses. So basically equation 7.122 from the book just basically said that the Lagrangian multiplier times the force of constraint with respect to x times the force of constraint equation with respect to x will give you the force of constraint in the x direction. Yeah, that's right. Also, the same thing here, it will give you the force of constraint in the y direction. So basically, this is our equation. This is our equation for the force constraint. we say x plus y minus c is going to give you the force. So basically, the derivative of this with respect to x would just be 1, and then also the same for y. So therefore, we get basically the force constraint in x direction is equal to our Lagrangian multiplier lambda. So therefore, with that, we know that lambda in the x direction, so tension on mass 1, which would be in the x direction, is just equal to m1x double dot, because that's what we got for our Lagrangian multiplier on the previous page. So also here we have tension in the y direction, which would be the tension of the string on mass 2, would once again just be the force constraint in the y direction, which is m2y double dot minus m2g, which ends up being m2 times y double dot minus g. So the last thing that the problem asks us to do is basically just use basic Newtonian approach to, just prove that our answer checks out. Like all that was a much more difficult way to solve this problem, considering the fact that there's a much easier way to just use basic Newtonian mechanics. But we wanted to do it with the Lagrangian approach. So basically just to show that that checks out of mass 1, basically we use Newton's second law, which is force is equal to mass times acceleration. So right here, so all the forces on mass 1 is equal to the mass times acceleration in x direction. So the only force on mass 1 that we know is tension, which is basically the string pulling on the mass, because there is no friction on the table. We already said it's a frictionless table. So yeah, tension is equal to mass times acceleration. Well, acceleration can be rewritten as x double dot. So therefore, that's the same thing we got. On the last page, we just had lambda is equal to x double dot, but we already said that lambda is equal to the force constraint in the x direction, which is tension. So therefore, tension is equal to mass times x double dot, and then we just went through the same process here with y. And that's pretty much it.